Hi everyone, welcome to the session on building human in the loop machine learning pipeline and MLOps. Before I get into the actual topic, let me introduce myself. My name is Abinaya Mahendiran. I currently work as a manager for the data science and applied AI teams at NextLabs Emphasis. My primary interest lies in building end-to-end NLP MLOps systems, and I also like contributing to open source. I also mentor at Springboard, and I do all the reviews for GHC, GHCA AML, sessions for GHC for a long time. So I have also provided my handles. Please feel free to get in touch if you have any questions. Let's get into the session. So for today, this is the agenda. Before diving into what the actual human in the loop machine learning is, I'll be providing an overview on what MLOps is and what are the pipelines do we have in MLOps. We'll address some of the data-centric challenges, and we'll see what human in the loop machine learning is, and we'll dive into all the methods that are available, and we'll also see an example for active learning. Once that is done, we'll see the other aspects of human in the loop machine learning like annotation and human computer interaction. I'll also share the links and resources that I have used for making this session at the end of the presentation. To start with, most of us would have heard the term MLOps, which is machine learning and operations. What DevOps is to a software project, MLOps is the same for a machine learning project. In a machine learning project, there are three dimensions that you need to take care of. One is the code, which can be versioned through any source control options. And second one is the model. And the third one is data. At every stage of the machine learning lifecycle, all these three aspects should be maintained and versioned. So when the data is available for us to build a machine learning model, essentially a data scientist will pick up the training data, build a model for the problem at hand, and he or she tests the model using the test data. Once the model evaluation and experimentation are completed, the data scientist might pick the best model, and that will be promoted to production. In the production phase, a machine learning engineer will basically package the model and expose it as an API after doing enough testing. So testing is done by using the testing data, and that particular tested model will be deployed to the application. Once the model is deployed to the application, it is available for the end users. The end users will start using your production model, and whatever data that comes in the real time will be kind of stored, and the model performance will be observed. If suppose the model performance comes down, again you will have to retrain your production model with more data so that the model stays stable all the time. So this is an iterative process, and this is very important in MLOps to maintain the entire code, model, and data at every stage. So this is what MLOps is. In any MLOps platform, there are certain pipelines that can be completely automated or maybe semi-automated. For example, an MLOps platform can have a data pipeline which is used to ingest data from several sources, and it can be standardized to a single format. Once that is done, we have a feature engineering pipeline where you pre-process the data, extract the relevant features for your problem, and you can save the metadata to a feature store. After the feature engineering is done, we basically start building models. You might have ready-made training and retraining pipelines through AutoML solutions, and you will be able to carry out a lot of experiments using different models or using different hyperparameters for the same model. Once all that experimentation is done in the development phase, you basically analyze the model, and you also version all the code data and the model in the model registry and source repository. Once the final model is picked up, you basically package it and deploy it through a model serving service, which is your inference pipeline. The basic idea of inference pipeline is to provide predictions on real-time data. There will also be a performance monitoring pipeline, which will keep monitoring the prediction model. And if in case the performance comes down, there will be a trigger to start the retraining. This entire lower side of the diagram shows the ML operations which we saw in the previous slide, and the upper side of the diagram is basically your development phase. If you look at it, all these pipelines are can be semi-automated or completely automated by available tools or frameworks. If you look at it, versioning, you have tools like DBC, ML Flow, and for code versioning, you always use Git. You can also have cloud provider platforms like Azure ML, Vertex AI, or AWS SageMaker. So there are a lot of ready-made tools that are available. So these are some of the essential pipelines that you need to have in any MLOps platform. Now let's see what are some of the data-centric challenges that we face in the industry. Most of the use cases that we deal with in the industry are all supervised in nature. That means you always need tagged data to solve the problem at hand. But getting the tagged data is a challenge. You may have to, hire annotators to perform annotation, which is actually a time-consuming and a costly task, because uh, sometimes you may need to build models faster. You may have to get better models in a short time. So there are a lot of constraints that we generally deal with in a real-time scenario. Once we perform annotation, the next step is to make sure whatever is the annotated data, the quality of the annotated data should be checked through any kind of feedback mechanism. Without this validation, the data shouldn't be used for building models, because only quality data will lead to better models. If we do not have good quality data, models will not be performing well in production. So this has to be kept in mind all the time. We may also need to build models faster, because we need to fail faster. If something doesn't work, we need to do it faster so that we can pick up the right things and move on. So for that reason, these days you have a transfer learning mechanism where you pick up a model in the same domain, but it might not be solving your problem, the problem that you're dealing with. But then you may leverage transfer learning and fine tune the model using some data. Which need not be a lot of data. With relatively less data, you will be able to build model faster. So these are some of the data-centric challenges that we face. But how do we make sure, we kind of use machine learning in assisting humans to solve these problems in the right way? That's where human in the loop machine learning comes into picture. So basically, human in the loop machine learning is a set of strategies that is used to combine human and machine intelligence so that model accuracy can be improved. Here we are trying to leverage ML to automate some of the processes that is involved in speed, that is involved in labeling. You try to speed up labeling, or you assist human in a certain way so that they don't have to start from scratch while they are trying to tag data. We also need to make sure that we always have the right set of data for annotation. Sometimes you may end up tagging data and use that to train your model, but then the model accuracy will not go up. So you should always employ some sampling strategies through active learning so that you always tag the right set of data that is in turn contributing to the improvement in the accuracy of the model. Like how choosing the right machine learning algorithm is important in solving your problem, choosing the right annotation strategy is also very important. These two decisions have to go hand in hand so that you can build better models faster. So if you look at this diagram, this provides an overview of how this process happens. So you have a production model and you have a pool of unlabeled data. Imagine the production model's performance is coming down. Now you have to improve this model by retraining. So what you do from this unlabeled pool of data, you employ some active learning strategies and you sample some data points for annotation. Then it goes to the human annotators where they label these items, and once they are labeled, after a validation, these data points are fed back to the model for retraining. This model basically is a fine-tuned model from a pre-trained model. So we are leveraging transfer learning here because this might be a use case in the same domain where we have a pre-trained model. So then you retrain this model and you deploy this model to production. And this is an iterative process if you look at it. Till the time you're satisfied with the accuracy of the model, or till the time the model performance is stable, this process has to be carried out. So this is an iterative process, and it may end at a point where you don't see any improvement in the model, or you think whatever accuracy is provided by the model is enough. So that's when this process will stop. Otherwise, this will keep continuing. Now we have seen that there are few aspects that we need to understand in human in the loop machine learning, which are active learning, annotation, and how to make sure humans and the computer are interacting in the right way. So first, let's look at the first aspect, which is active learning. Active learning is nothing but the process in which you decide what sample has to be taken for human annotation. So this is basically sampling strategy. Like I said, this is an iterative process. It will keep improving your model accuracy. So you will do this in iterations. Some of the general methods that are available are uncertainty sampling, this diversity sampling, and random sampling. In uncertainty sampling, you basically try to find data points that are close to the decision boundary. So if you look at this diagram, this is an example of a binary classification problem where you have just two classes. The model is predicting, and this is the decision boundary of the model. And if you see, there are some data points that are close to the decision boundary where the model is not very confident in making predictions. So in uncertainty sampling, you will employ techniques where you will sample the points that are near to the decision boundary. In diversity sampling, we try to identify the outliers of the model, and we try to pick those outliers for sampling, because sometimes the model will not know in its current state, it might not know what items are important and what data points are not important. So in that scenario, diversity sampling will help in sampling the right data points that resemble real-time data. So that is what diversity sampling does. Uncertainty sampling is an exploitation strategy where you try to get the samples from a similar space in the distribution. Whereas in diversity sampling, you try to explore a lot of space in the domain. So that's why this is an exploitation and exploration strategy, respectively. And the next one is the random sampling method, where you sample the data points randomly. This can be the simplest case. So either you can use methods under uncertainty sampling and diversity sampling individually, or you can combine any two methods that you find fit based on the problem at hand. Whatever methods you choose, random sampling can be baseline. So you build a model using data points tagged through random sampling, keep that as a baseline, and use the other model's performance to compare it with the random sampling model. So that way you will have an idea of how well other techniques are performing. Now let's look a little deeper into the different types of sampling techniques that we have seen. First one is uncertainty sampling. In uncertainty sampling, basically we try to calculate something called an uncertainty score. The score is always between 0 and 1. If it is closer to 1, that means the model is highly uncertain of its prediction. So you may have to sample those points with high uncertainty score. If it is a low uncertainty score, then the model is very confident in predicting those data points. Then you don't have to worry about those data points. The first method under uncertainty sampling is least confidence sampling. Here, you try to calculate the difference between the most confident prediction and 100% confidence. So basically, there are, say, n classes. out of which one class has the highest probability, 90, say 90%. In that case, you subtract 1 minus 0.9 into n divided by n minus 1, where n is the number of classes. You will get the value of uncertainty. If this value is close to 1, then you need to sample those data points. If this value is closer to 0, then you may not need to sample those points. So that is what least confidence samples. In margin of confidence sampling, you take the most confident predictions, two most confident predictions. Say y1 is the most confident prediction and y2 is the second most confident prediction. You find the difference between the two and you normalize it by subtracting from 1. So even here the value will range from 0 to 1. If the data point is close to 1, you sample it, otherwise you don't sample it. Ratio of confidence method is where you calculate the ratio between two most confident predictions. So this is similar to the previous one, except that we are dividing the second most confident probability by the most confident probability. So this will also give you a value between 0 and 1. The last method available under uncertainty sampling is entropy-based sampling. Here, difference between all the predictions are calculated according to information theory. You calculate the negative log of the probability into the actual probability and you sum over everything and you divide it by log n to normalize it. So here, if the data point has high entropy, that means you need to sample the data point. Otherwise, if it has low entropy, then you don't need to sample them. So these are some of the methods that are available under uncertainty sampling, and this can be implemented. And all the implementations are available on a GitHub repo. I will be sharing that also in the end of the presentation. So you can have a look at it if you want to. The next method that we saw was diversity sampling. Even under diversity sampling, you have 4 different methods. The first one is model-based outlier sampling. Here, what we want to do is we want to sample the data points which has low activations in the last layer. So before the output layer, there will be a hidden layer, right? So in the hidden layer, whichever data points, whichever classes have less activation, you will pick those data points for tagging. The second one is cluster-based sampling. Here you split the unlabeled data into clusters first. Once you make them as a cluster, you can either use some distance metric, like you can either pick the centroids from each of the cluster for labeling, or you may even pick the outlier of the centroids for labeling, or you may use some random choice to pick the data points within the clusters. So these are some of the variations under cluster-based sampling that you can use to sample the data points for tagging. The next is representative sampling. So in any real world scenario, the place where you're going to deploy your model, the data distribution there might be different from the actual training data distribution. So this is a very normal occurrence. So in this method, what we try to do is we try to find the items that are most representative of the target application. So this way we try to make a model robust enough to generalize. So this is what representative sampling does. The last one under diversity sampling is sampling for real world diversity. So here, say for example, you have a problem where you have to deal with, say, age or gender. You have metrics related to sensitive information. So all these things, you will have to make sure that you increase the fairness with the data by supporting the real world diversity. So this is what sampling for real world diversity does. So if you look at this diagram, you see that there are some demographic features and you try to sample from all the different demographics, not just concentrating on, say, one particular gender or one particular location. You will try to diversify your sample by taking samples from all the demographics available. So this is what diversity sampling is. There are more advanced techniques that are available, but I'm not covering all those advanced techniques here. I have covered only the basic methods here. If you want to have a look at all the like advanced methods, it is available in the book. So I provide, anyway, I provided the link. You can go through that. Now that we have understood the first aspect, the active learning, what is active learning in the human in the loop machine learning pipeline, how do we make sure when to choose which sampling strategy? So for that, you can use this as a checklist. Any machine learning model that you have, it might have some known knowns. So that means it might be confident on whatever predictions that it is making. But there are scenarios where the model is not sure of what it is predicting. So that belongs to known unknowns category, where it is confused. So for example, we saw the example of uncertainty sampling, right, where the points near the decision boundary is not very clear for the model. So in this case, you will use uncertainty sampling techniques, and then you can solve this problem. There are scenarios where the model isn't aware of what it knows. Maybe it is from a domain where we have pre-trained models already available. So what we can do is we can use those pre-trained models and fine-tune it for the downstream task that we are dealing with, and then leverage it by using transfer learning. So this way you will be able to tackle the unknown knowns. But there is one more scenario where the model is not sure of what it doesn't know. Then you can use diversity sampling. So you may have to bring in other mechanisms to augment your training data, and you need to annotate using your diversity sampling techniques. That way you will be able to address this quadrant as well. So this will give you an idea of when to use which method. Now, let's see an actual example of active learning in text classification. So this was a small side project that I have done for a course along with a partner. So this is available on GitHub repo, and I provided the link as well. So main objective of this example is to show you how to implement the basic techniques that I have explained in the previous slides for a text classification problem. So what we are trying to do here is we need to classify the news articles. These news articles are present in Kaggle. A corpus, like a selective corpus is available in Kaggle, but the actual data has like 4 million data points. But on Kaggle, it has 120K data points. So if you see, this particular problem has 4 different classes: world news, sports news, business news, and science and technology news. What we are trying to do is classify the news article's title into one of these 4 categories. The total number of data that is available is 120K for training and 7.6K for testing. That 7.6K test data is kept aside so that the model can be evaluated on it. This 120K training data will be split into several subsections based on the experiments that I'll explain that in a minute. For this problem, we have leveraged transfer learning. So we used a pre-trained Roberta model. Roberta model is available in Hugging Face, and it is trained on a huge English corpus. So this can be used directly to fine-tune on this downstream task. And this model is fine-tuned on out of this 120K, we have taken 96K as the training data, and remaining 24K is kept for validation. So as a baseline, 96K data points are used for fine tuning the Robert model. All the data that is available is already tagged. But for the sake of this experimentation, we will set aside some data for sampling, and then we will retag it and see if whatever the existing tags that the data has is correct or not, and then we evaluated the results. Then for this experiment, we have three different data regimes. One is high, medium, and low. In high data regime, what we are doing is, out of this 96K, we keep 30K as the training data and we fine tune the model. 24K remains as the validation set, where we fine tune the model hyperparameters, and the remaining 66K data is available for annotation. From this, we will pick up samples through different sampling strategies like sampling, uncertainty sampling, and diversity sampling, and we will be evaluating this. In medium data regime, we have like just 6K data points, and validation data remains same. And there are some unused points. We are not telling this. We still use the same 6K. Similarly, in low data regime, we just start with 1,000 data points to fine tune the model. So the idea here is to answer some of the questions that we have. One is, how much of data is needed to fine tune the model and give better results through active learning, and when to stop the active learning. So there may be scenarios where you keep doing this active learning process and your model accuracy keeps increasing. But there may be a point where where the accuracy of the model doesn't increase. So how do you find out when to stop active learning? And what sampling method is best for the use case at hand? So we wanted to answer these questions, and this experiment is designed to address these questions. So now let's see the result of this experimentation. We were able to carry out some 13 experiments. All the details are available in the report, but here I have just kept only the high data regime and low data regime results. So here, if you see in the low data, let's look at the low data regime first. Here we have calculated baseline accuracy. If you see here, it is 6.9% is the test accuracy. But the overall model with this, which is trained on 96K data points, had the highest accuracy. But this baseline, since it is a subset of data is used for training this model, it has a lower accuracy. And this is our baseline for this method, for this low data. It was just trained on 1,000 samples. Then we used random sampling, entropy sampling, and least confidence sampling, and we did the training. And we did only 200 annotated samples at each cycle. And then if you see, the baseline is 86.9%, but the least confidence method gave 88.5%, which is pretty close, better than the other two models. So in this particular scenario, we found that like when the data is less, least confidence sampling gave better results for our problem. In high data regime, if you see, the original model, which was trained on almost all the data that is available, has the highest accuracy, whereas the baseline, the 30,000 data points, had almost closer accuracy to the original model. Still, we carried out our experimentation with other kind of sampling, and we got results that are kind of similar to the baseline. So in this, kind of shows that in some scenarios where your model is trained with a huge amount of data, learning might not result in a huge improvement. It may be okay, like it might give you say 0.1 or maybe less than 1%, or maybe even less than 5% improvement in accuracy. But depending on the use case, maybe that might not be even needed. The accuracy you already have might be enough. So from our experiment, what we realized is that high data regime does not even need active learning. So it can work well with fine tuning and data cleaning steps. So that is what we have observed in this experiment. The detailed report is available in this link. Please feel free to have a look at it. Now we have understood the first aspect, which is active learning in the human in the loop machine learning. Now let's see the second aspect, which is annotation. What is annotation? annotation is the process of creating the training data for the model. So you need to employ people to do the work for you. Based on that, based on certain aspects, you will decide on whom to hire. So, for example, if the task is complex or simple, you may need specialized people, to do the task. If it is an urgent task, you need more people to scale the solution up. Then you may go for a specific type of work. So based on these three aspects, task, urgency, and scale, you will determine the type of workforce needed for annotation. There are three types of workers. One is crowdsourced workers, contract workers, and in-house experts. Crowdsourced workers can actually, produce results faster, and they might be able to, work for a short period, but they might produce more quantity. So that's what crowdsourced workers will do. Whereas contract workers can work for a longer duration, but they might be able to produce little less quantity than the crowdsourced because they might need specialized training, or they might not have the domain knowledge for which they are annotating the data. So because of all those other constraints, they may be producing less output. The third type of workforce is your in-house experts. In-house experts are the subject matter experts who will provide their inputs in case of corner cases or edge cases. Like say the contract worker or a crowdsourced worker has tagged some data points, but they are not very sure of their whatever tags they have given. So in that scenario, you bring in a subject matter expert, and he or she might be able to provide better tags to that particular data point because they know in and out of the domain. So these are the types of workers that you can hire to perform annotation. How do you make sure that the data that you annotate is of good quality? By making sure that you adhere to the principles of good data annotation, which is pay the workers fairly. Making sure that they get the right incentives will keep them happy, and in turn they will give you quality work. Second is security. So you should make sure that you treat your contract workers also like a full-time employee. So that way they will feel that they are part of the team, and they will be not worried about other things, monetary things, and they will be able to produce good results. Similarly, providing transparency. So it is always good to set your objectives transparent, so that people who are not part of your team but are working for a contract or for a short period of time, they also understand what they are contributing to. Their contributions are also valuable. We just have to make sure that they know it, so that way they will produce better results. Now that we've seen about the workforce that is needed for performing the annotation, when do we actually stop annotating the data? Because this cannot go on for a long time, right? At some point, you have to decide, okay, what I have is enough. How do we do that? For that, you have something called orders of magnitude principle. So take any machine learning model. Even if you blindly build a model, is it is as good as the prediction of the model is as good as tossing a coin. So it has 50% chance that it will predict the data point correctly. So imagine that is your baseline. If you want to achieve a better result than a chance, which is a meaningful signal, you may have to tag at least 10 power n data points. N here represents the number of classes in your problem. Say if it is a binary classification problem, you need to tag at least 100 points to get a meaningful model than a baseline model. But that accuracy is definitely not enough. If you want to make that accuracy a bit more consistent, then you need to tag at least 1,000 data points and then retrain the model. But this accuracy is also low, but it is consistently increasing. In that scenario, you will kind of increase the tagging to 10, say here you said 1,000, so it will be 10,000. So yeah, after 10,000 points, you may get a model that has good accuracy, and you might be satisfied with that accuracy, and you can even deploy the model. But there might be scenarios where you might need to have like really high accuracy models. Then you go for the state of the art models, where you actually need more data. You might need to tag 1 million data points to get state of the art model accuracy. So this decision is on us. It's on the business to understand what they want, and they can stop at the point where they think they have reached the required metric. So this is what you need to do in order to understand when to stop annotation. Now let's look at the final aspect in the human machine learning pipeline, which is human computer interaction. We of course need to build an interface where you actually showcase the data to the user with all the instructions, so that he or she can annotate the data. So you have to make sure the human computer interaction is effortless, and it needs to stick to certain characteristics. So first one is affordance. So whatever interface you are building, it has to work in a way the user perceives it to work. So you need to make sure that the user understands the interface in an intuitive way. If that is not there, the annotation will not be effective. The next aspect is feedback. So the user should be able to provide feedback through your UI. This basically complements the affordance. It validates the affordance, because if something is not working as expected, either the assumption made by the user is wrong, or the actual problem is with the function itself. So in this scenario, the user should be able to provide feedback. The interface should also have an aspect called agency. Means it should give a sense of power to the user, that they have ownership over the platform. So they should feel good, that that I have control over this platform, and I'm able to do whatever I want. So these three characteristics should be present any of the interfaces that you build. You can choose any technology to build it, but it needs to adhere to these aspects. Whatever interface you build, it might fall into one of these four types. One is unassisted annotation. In this type of interface, you will not have any involvement of machine learning. This is just plain interface, and the user will be able to do whatever they want. They'll be able to add, edit, or delete data points. They have full control over it. So if you see here, it has good, the quality of the data will be good because it is done completely by humans, but it will be not very efficient because it is kind of time consuming, and the user will have more control over the interface itself. And implementation effort for the interface is also less, because it's very straightforward to put together say a HTML page to capture the user input. The next type is assisted annotation. In this kind of interface, you have a machine learning model assisting the humans. So this is like a little bit of automation is involved. So the efficiency is little neutral, better than unassisted annotation, but the quality is also good, and the user will have a better control. Now they don't have to start from scratch; they have something to start with. And the implementation is worst in the sense you need to put together a mechanism to handle the machine learning models, and then the user should also be able to interact with the interact easily with the interface. So that is what assisted annotation interface means. If an interface falls under predictive annotation type, here the machine learning model generates the candidates that can be edited. So the user need not you know go through all the data. Instead, whatever data is shown by the machine learning model, the user will be editing that. Here efficiency will be good because the model itself shows what needs to be edited, but quality might go for a toss. If the model is not good, then the quality of this data might be bad, and it has like neutral, the user will feel that he has like okayish control, so the agency is neutral and implementation effort is also kind of neutral. In adjudication type of interface, the annotator will have no control on the interface. The machine learning model will show only the data. He can either data with tags, and he can only check it, and he cannot even edit it. Efficiency is good because they'll be able to, plug a lot of points, but quality might be okay. It is dependent, and they have no control over the interface. And implementation effort is also uh, like kind of good. So these are some of the types under which you can build interface. So even this decision is up to the business. So what you want out of this interface, you can design the interface accordingly, but this will provide a way for the humans to leverage machine learning in a better way. So this is the final aspect in human in the loop machine learning. So I think that brings me to the end of the presentation. So here, all the material that I have covered in this entire presentation is taken from this book. I highly recommend you all to go through this book. So the name of the book is Human in the Loop Machine Learning by Robert Monroe. He also has put up a corresponding GitHub repository where advanced techniques are available. What I have shown in the presentation is the basic techniques, but there are advanced techniques that uses transfer learning also. You can check out this repository and the accompanying blog post. The experiment that I have shown in the presentation is present in my GitHub repository. I have also provided the report link in the actual slide. You may go through that in detail. Apart from that, I also provided some links where you can find courses on active learning. Because it is actually an emerging area, and you will have to invest a lot in making your data stable, right? So it is good to go through these links and find some courses that interest you. Yeah, so this is the resources that I would like to share. That brings me to the end of the presentation. Thank you so much for attending this session. Very happy Women's Day to all of you. Please feel free to reach me through any of my social media handles. I would be happy to answer any of your questions. Thank you.